Okay, so let's try to put all those pieces together and do an example. A national report stated that the mean number of years of nursing experience among the nursing staff was 14.3 years. A nurse manager took a survey of a random sample of 35 nurses at the hospital and found a sample mean of 18.37 years with a standard deviation of 11.12 years. Do we have evidence that the mean years of experience among the nursing staff at the hospital has increased? Now, before you start thinking, well, duh, 18.7 is greater than 14.3, of course it increased. Remember that she didn't survey every single nurse. She took a sample. And so the question is that sample mean so much greater than 14.3 that it will give us evidence that if they were to survey the entire nursing staff, they would get a number that was greater than 14.3, that the value really has increased. Okay, so let's go ahead and get started. So we start with our hypotheses. So our null hypothesis is that the mean has not increased. It's still the same. It's still the status quo. Now, this is a symbol for mean. It's a Greek letter M, all right, M for mean. So the mean is still 14.3. But our alternative, what we think might have happened, is that the mean has increased. In other words, the mean is now greater than 14.3. All right, so that's step number one, our hypotheses. Now, let's talk about behind the scenes, like, well, how are we going to figure this out? Do you remember that last week we did something called the CLT, the central limit theorem? And what we said then, or what I said then, was that the CLT was the basis of all statistical inference. So we're going to revisit that for just a moment, okay? So remember, what did the CLT say? The CLT said that under certain circumstances, and again, our sample size large is one of those circumstances, no matter what our parent population looks like, if we take a large enough sample and we find the mean of the sample, and then we graph it, and we do that over and over and over again, we know that the sample means are going to have this shape. They're going to be centered at the population mean, which we are assuming is 14.3. And the spread, or the standard, they call it the standard error. We didn't talk about that, but the spread, the standard deviation of the sampling distribution is going to be equal to sigma over the square root of n. Now we know our sample size is 35, so we would be dividing by the square root of 35, but here we run into a problem. All right, you might not even realize it's a problem. This number here, we don't know what that is. That stands for, remember, the population standard deviation. And in this problem, we're not given the population standard deviation. You might say, well, wait, there's a standard deviation right here. Yes, there's a standard deviation right here, but that's the standard deviation of the sample. This is the sample standard deviation. We don't know the population standard deviation. So you might say to yourself, well, aren't they close enough? Can't we just swap them? Put one in for the other? Couldn't we just say, well, I don't know this one, but I do know the sample standard deviation. I'll just put that there instead. Very tempting. And that actually really is kind of what we do, except when we do that, one small modification has to be made. Okay, so here's the modification. So when you do that, when you substitute S, the sample standard deviation, for the population standard deviation, which is unknown, when you make that swap, we no longer have a normal distribution. We have something called the t distribution. Now you're going to be saying, wait, that's a normal distribution. It looks just like a normal distribution. True, it does. However, so what's similar? It's symmetric and unimodal like the normal distribution, but the tails are slightly thicker. All right, you can see here they're just a little bit thicker in the tails than a normal distribution. And each curve has associated with it a number called the degrees of freedom, which is abbreviated DF. And as the degrees of freedom increases, the tails tend to thin out. So here's some pictures, all right? So this is a picture of the normal distribution and the t-distribution when you have 40 degrees of freedom. So you can see that those curves look exactly the same. But here, you can see a normal distribution and a t-distribution when you only have 1 degree of freedom. And you can really see there that the tails are different for the two curves. But as the sample size increases, the t-distribution becomes more and more like a normal curve. And for tests involving means, the degrees of freedom is equal to n minus 1. In other words, a sample size minus 1. So that's a little bit of behind the scenes about the t-distribution, and that's why these are called t-tests. Okay, so our null hypothesis, again, was that there's no change, that the mean was still 14.3. Our alternative is that the mean has increased. The mean is equal to or greater than 14.3. That's what we want to determine. Now we are going to use what we call a t-test because we're doing a test claim about a population mean. So picture-wise, we have a t-distribution, which I know looks just like a normal distribution. Next, we would find the test statistic and p-value. So again, getting back to this picture here, we would have this, we would use the standard deviation of 11.12 here over the square root of 35. Now, if we were to compute that, let me just pull out a calculator and do that for us quickly. Divided by the square root of 35. That comes out to be 1.88. Okay, so our distribution then would look like this. A sample of a mean of 14.3 and a spread, a standard deviation of 1.88. And our sample is 18.37. And the question is this unusual? This area right here is our p-value. Now, we could find the test statistic and find the p-value using a formula. And again, it wouldn't be that hard. The test statistic is in the form of a z-score, right? So it'd be our number. Here, let me try to be a little more neat. It would be our test value, 18.37, minus the mean, divided by the spread. And that's our test statistic. But we could just use technology and do it as well. So if you were to use technology and do that, we find a test statistic of 2.17 and a p-value of 0.019. So in other words, we're over 2 standard deviations from our center, and our p-value here is very small, 0.019, less than 2%. So if the null hypothesis were true, there would be less than a 2% chance of getting the sample that we have. All right, so again, what would we think? We would think that this is very unusual, very small. So we would reject the null hypothesis, and our conclusion would be that the mean years of experience has increased. Let's see if we can look at another example. All right. So previous studies have shown that the average time a person spends on social media daily is 2 hours. A researcher wants to test whether new parents spend more or less time daily on social media. Assume that the distribution of the amount of time is approximately normal. Now, the reason that that sentence is important is because when we look at our data, we can see that we don't have a large sample. We have a rather small sample. So here's our data. So she's recorded the social media use of new parents, and there's her data. Can she conclude that news parents spend more or less time on social media than the national average? Okay, so our null hypothesis is that the mean is 2 hours. And the alternative, what we're trying to investigate, is whether that mean is more or less than 2 hours. In other words, is it different from 2 hours? Okay? We know that the parent population is normal, so it doesn't matter what our sample size is. So we're going to go ahead and we're going to use a t-test to determine whether we believe the null hypothesis or we believe the alternative is true. Okay. The test statistic and p-value, I'm not going to go into drawing the picture. I'm not going to go into the formula. We're just going to say, okay, we used technology and we found it. So the sample mean is 1.6. The sample standard deviation is 1.40. So if you put these numbers into a statistical calculator, you could find this out. And the sample size is 15. Okay. So using technology, our test statistic comes out to be 1.1, negative 1.1, and our p-value is 0.29. So here's the idea. We have a t-distribution. Our hypothesized center was 2. And we have a test statistic which is just a little over 1 standard deviation to the left. And this area here is 0.29. So is 0.29 a small number? And again, how do we know if something's large or small? We compare it with the significance level. So 0.29 is not small. It's not less than our alpha. It's not less than 0.05. So we're not going to reject the null hypothesis. So we don't have any evidence that new parents spend significantly different amount of time on social media than the rest of the public. So we have no evidence that new parents time on social media differs from the population. In other words, differs from 2 hours. Okay? All right.